Hey guys, in this lesson we're going to study how to review identifying redox reactions, and then we'll talk about half reactions specifically, including writing them and also identifying one that's balanced. The homework that's going to be due with this lesson is questions 32 through 34 on page 164, and there is a quiz associated with this lesson, so make sure you've been studying the last few lectures as you prepare for the quiz. Our aim today is what are half reactions. That's the most important thing we're going to study. And please copy down these do now questions. You don't have to copy down all of these words. A lot of it is repeated, but at least copy down the meat of each question so that you know what we're doing as soon as class begins. All right, as a review, there are two things you can do when you're trying to identify a redox reaction. Firstly, you should check to see if there is an uncombined element on one side of the reaction that's combined with another element on the other side of the reaction. Because if that happens, what you know has occurred is redox. Here's the reason why. Basically, uncombined elements have an oxidation state of 0 by definition, so combined elements have a non-zero oxidation state by definition. And if you have something that's uncombined on one side and combined on the other, then obviously it's going from 0 to non-zero. So that means that electrons have moved around and that redox has definitely occurred. Now the other option is whether or not you can identify a double replacement reaction. If you can identify a double replacement reaction, you should know that redox has not occurred. And we know this because in a double replacement reaction, ions get shuffled around, but electrons do not. But there are rare circumstances when neither one of these shortcuts will work. And if that's true, then what you need to do is you need to assign oxidation states to all the elements in the reaction in the hopes of finding an element that has changed its oxidation state. So let's go ahead and do that now. Chlorine is a halogen in group 17, so that's always going to be -1. And the hydrogen in this case would have to be +1. Oxygen is -2, and what is that? That's -2 times 3 is -6, so this is the -6 right here. Calcium is going to be +2, and -6 plus 2 is -4. So this carbon must be +4. Chlorine is -1, but there are 2 of them, so that's -2, which makes sense since this calcium must be +2. Oxygen is -2, and these hydrogens are +1. Oxygens are -2, and this carbon is +4. So I'm checking for any oxidation state which has changed. The hydrogens aren't changing, the chlorides aren't changing, the calciums aren't changing, the oxygens aren't changing, and the carbon stayed the same as well. So is the reaction above redox? No. None of the oxidation states changed. All right, so there is a certain importance to a half reaction. Let's take a look at this full reaction to get some context. So what information is given in a reaction equation such as copper plus silver nitrate yields copper nitrate and silver. So you get information about the elements involved, but also their amounts and their molar relationships to each other. But what they don't show is anything about electrons. And as we study oxidation reduction, you probably have noticed that we talk a lot about electrons. So I think it's ironic that the full redox reaction, which you see here, is not actually inclusive of the one thing that we care about, electrons. And in order to get this particular information, we need to use half reactions. So what are those? There are oxidation half reactions and there are reduction half reactions. Here is an example of both. So here's our full oxidation reduction, like full reaction. We have a copper plus a silver nitrate yielding a copper nitrate and silver. And you can think of this as two different reactions. You could think of it as the copper who is getting a new charge and the silver who's getting a new charge. to help reveal all of that, I'm going to do this the long way and show you the oxidation states. So this copper is free, so it's going to be a 0. Nitrates are -1 and polyatomic ions, and I notice that it's the same on both sides, so we'll end up leaving that out of our equation as a spectator ion. So I highlighted in black for the spectator ions there. But in any case, this nitrate was a -1, which means that I know the charge of the silver right next to it. That silver is +1. And over on the other side, we have nitrates -1, but there are 2 of them. So that means that this copper must be +2. And then this silver is a 0 because it's going to be uncombined. So that's why in this first reaction down here, I have a copper, which you'll see here, becoming a copper 2, which you'll see there. And I also added 2 electrons, and here's the reason why. The charge on this copper had to have been 0. And then to get from 0 to +2, you have to release 2 electrons. And as a double check for that, you can think of it like this. -2 plus +2 equals 0, which is certainly true, and that's a requirement of all half reactions, is that you have the same total charge on the right and the left. In this case, the total charge was 0 on the right and the left, but it doesn't have to be, it just was in this case. They just need to be the same. Let me show you the next one as well. So we have a +1 for this silver, and electrons are -1. +1 minus 1 is 0, which makes sense for the silver on the right-hand side, which is uncombined, so that would be 0 as well. So total charge on the right is 0, and the total charge on the left is also 0. And one more time, it does not matter if the total charge is not 0. The total charges need to be the same on the left and the right. So let's identify each of these as either oxidation or reduction. So the easiest way to do this is just to say that if you can find the electrons on the right of a balanced half reaction, then it's oxidation because it's showing loss. Now here are the oxidations on the right-hand side of this reaction. So this is going to be oxidation, it's showing loss. But there is another way to tell, which is that the charge goes from 0 to +2. So if the charge increases, then that's also oxidation. So I've got my oxidation half reaction in there. And then on the second one, what we've got is a +1 ion, and it seems to be absorbing an electron to make this neutral silver. So one thing I can point out is that we do have electrons on the left. That means reduction because it's showing a gaining of electrons. But there's one more bit, which is that a reduction reaction is one where the oxidation state decreases. And if you go from +1 to 0, that is certainly a decrease. So there's your 2 reasons that it's reduction, electrons on the left, and the oxidation state goes down. So these are half reactions, and what they're really good at is showing you the pathway that electrons take in a redox reaction. And the spectator ion was nitrate, and that's it for this slide. All right, so let's learn how to write our own half reactions. So step 1 is assign oxidation states to every element. You may omit spectator ions if you can identify them. And I'm just taking a quick glance, and I can see that nitrate is a spectator ion along with that one. Otherwise, they all look real and useful, so I'm going to start putting in oxidation states now. Zinc is an uncombined element, so its oxidation state is 0. Nitrates are -1, and I see that we have 2 of them, so that's going to be a total of -2, and that means that this lead is +2. This lead right here is going to be 0 because it's uncombined, and I know that nitrates are -1, and there are 2 of them, so I'll put in the -1, but -1 times 2 is -2, and that means that this zinc is +2. Now remember what I said. An oxidation half reaction is going to have electrons on the right, and you'll notice that the oxidation state increases. So in my analysis, I can see that zinc starts at 0 and ends at +2. So that to me proves that that's going to be the oxidation. So I'll just go ahead and write zinc, a little bit of space, arrow, a little bit of space, and then write Zn plus 2. So this is the beginning of my oxidation reaction, but I need to show electrons in appropriate places. Remember, oxidation reactions have electrons on the right. So let me put in some electrons. And lastly, I need to observe this rule about balancing my half reactions. So I need to say that there were 2 electrons. And the reason for that is -2 plus 2 equals 0. All right, now let's identify the reduction reaction. You'll notice that the reduction half reaction will have an oxidation state which decreases over time. And in the full reaction, I can see that that's happening to lead-2. Lead-2 is becoming lead-0 over time. So the oxidation number decreases, and I can go ahead and start this one out. So start out with lead-2, leave a little bit of space, put an arrow, and then end with lead. Now the second thing about reduction reactions is that the electrons are going to be on the left. So let me go ahead and show those. I need to have the electrons on the left right here, and there is a certain number I need to show, which in this case is, I should probably show 2, because I have a +2 and I can have -2, and it can be equal to 0 for that lead. So let me put in 2 electrons here, and then I think we're done. So I've already included the electrons. I got ahead of myself. That's what I should have done down here. I'll just rewrite my equations more neatly. So I've gone ahead and highlighted the electrons to just really sort of hammer home that in an oxidation reaction, electrons are on the right, and in a reduction reaction, electrons are on the left. The spectator ion, as I had already discussed almost immediately, in this case was nitrate. Polyatomic ions are usually going to be spectators. Now we need to be able to identify a balanced redox reaction when we see one. We don't have to know how to balance them ourselves, which is lucky. But we do need to say that the law of conservation is going to show that you always have an equal charge on the left and the right of a reaction. So then what's really being balanced is the electrons, which are our charges. So reactants and products must have equal net charge, both left and right. So which of the following redox reactions is correctly balanced? I can assign oxidation states to help with this. So we have a 3 from this iron, a 0 from that nickel. We have a +2 from this iron, and +4 from this nickel, because it's 2 times 2. And just combining, I have a +3 on the left, and +6 on the right, and those 2 numbers are not equal, so that's not the answer. The next one, I have +6 from this iron, a 0 from this nickel, +4 from this iron, and +2 from this nickel. Combining, I have +6 and +6. These 2 numbers are equal, and so that's probably the answer. In the next one, I have +3 for the iron, 0 for the nickel, +2 for the iron, and +2 for the nickel. Combining, I have +3 on the left and +4 on the right, not equal. Last one, I have +4 from the iron, 0 from the nickel, +4 from this iron, and +4 from this nickel. As I combine, I get a +8 on the right and a +4 on the left, and those 2 numbers are not equal. So let's say that I didn't know beforehand, and I just were finding out now. This would be the right answer. So that one's balanced because it's showing a conservation of charge, +6, +6. All right, and with that, we have finally reached our pair up. So please copy down these questions before class tomorrow. Follow them with this summary, and thank you so much for watching.